Integration by parts is, again, one of those things that just takes practice. And if you look up on YouTube, there's different strategies and things. And through the years, I've kind of settled on the easiest way to come up with your integration by parts recipe here is to start with dv. So our goal, when we're looking at this, we're looking at the integrand, and we know right away the dx has to come over here. So the left-hand column, we're going to be differentiating u. The right-hand column, we're going to be integrating dv. In order to integrate, we have to have a dv and a d. We have to have a differential on both sides. So we know that that's where we're at. So there's only two factors in here. We've got this x squared, and we've got this natural log of x. So one of them's going to go in one place, one's going to go in the other. And I think that the best way to sort of triage this is to look at the integrand and say, what is the largest piece that's easily integrable? You know, easy in quotes. That's readily integrable. And so we could put natural log there, and we did see on Tuesday that we can integrate natural log, but it's kind of a complicated antiderivative. X ln x minus x. You could do that. But usually what we are saying, when I say the word easily integrable, x squared is more easily integrable than natural log of x. So this would be the natural choice. The natural choice would be to separate your product into that. So what we are doing is taking everything in the integrand, including the differential, and we're breaking it apart into a u and a dv. And again, in the big picture, most of us think of integration by parts as a reverse product rule. It's how you integrate a product. You know, the product rule was how you differentiated a product, and now we're trying to integrate a product. And when we say product, we mean it loosely. Like if we see natural log of x over x squared, that's still a product. It's natural log times 1 over x squared. So there's a product, and we're trying to integrate this product. And so this would be a natural choice here. Natural log differentiates really easily. This is going to be 1 over x dx, and I'll just write it as dx over x. And then integrating x squared, we get x cubed over 3. And again, with integration by parts, when you're doing this dv, you can always choose your constant of integration to be 0. You don't have to worry about writing that as x cubed over 3 plus c. If you wanted to put a constant of integration in there, you could. You could put plus pi if you wanted it. Keep things as simple as possible. Choose c to be 0. So now we're ready to roll with our integration by parts formula. And this is where we use the ultraviolet voodoo as our memory trick. Ultraviolet. Ultraviolet means u times v. So we're going to take these two, multiply those two. U times v. So that's going to be 1/3 x cubed times natural log of x. So uv minus the integral of voodoo. Voodoo is the bottom row. All right, so that's going to be x cubed divided by 3. There's v. du is 1 over x times dx. So we're going to have that. And here is where we make the assessment of whether we did a decent job of picking the u and the dv. If the integral that we get there isn't easier than the original integral, if it's harder, then we definitely mischose our u and our dv, and we go back to the drawing board and try something else. So this integral is kind of our checkpoint. We look at that, and if that's easier than the original, then we're most likely cruising in the right direction. All right?
What's the formula look like? Like we do?
The integration by parts formula? Right there. uv minus integral of v du. Ultraviolet voodoo. So that's kind of the acronym or whatever that's called, the word trick that we use to memorize. And clearly that integral is easier, right? We can cancel out an x. So that's going to be much easier. So we're going to have 1/3 x cubed natural log of x minus, and if we cancel out an x here, this x is going to go away, and that's going to become a power of 2. And we just integrate that square. Add 1 to the exponent, divide by the new exponent. So that's going to put us right where we want to be. So that's going to be x cubed divided by 9, or we could write that as 1/9 x cubed plus c. So that's kind of a classic integration by parts. It has the traditional form of a product, which is how we generally think of integration by parts. It's a reverse product rule. It's how you integrate a product. And that's our process. Okay, so at the end of class last time, I mentioned that there are problems where you have to use integration by parts more than once. So we have repeated integration by parts. Now we went through this slide already, so another kind of nuance of integration by parts is that sometimes you can use it to integrate not products, like inverse sine, inverse tangent, inverse secant, all those inverse trig functions, natural log function. Those aren't products, but this technique does actually work for those as well. So that's kind of neat. It's got a wide range of problems that you can use integration by parts for. Here's another classic one. We clearly have a product. So when we look in here, we see this x squared, and we see this natural log of x squared. And that notation that you see there is kind of a newer thing. 5 years ago, you wouldn't have seen that in a textbook, but they're starting to do that more frequently. Normally, normally when you see natural log squared, this is, that's the traditional notation. They're kind of using that trig notation shortcut here, which is a newer thing. But again, it means this. So just remember, if you were to differentiate this, you would have to use the power rule followed by the chain rule. Okay, so let's set up our little table. So UdV, that's what we're trying to break the integrand into. And we're going to want to pick the biggest chunk of that integrand that's easily integrable. Well, as soon as we see the natural log, we should flinch. We should go to the other part of the integrand for your dv. When you see natural log, you do not want it with dv unless you absolutely had to. So this is going to be our natural choice. And I'm going to write that natural log over here like that because that's going to probably be a little bit more obvious how to differentiate it and not get screwed up with the exponents. So du is the derivative over here, so we have to use the chain rule. So this is going to be 2 natural log of x raised to the 1 power. Bring down the power, leave the base alone, subtract 1. Power down, subtract 1. And now we have to differentiate the base. So the base is what's in parentheses for our exponential expression there. The derivative of natural log of x is 1 divided by x, and then we have to put a dx in here as well. So there is du. And we've chosen x squared over here for dv, so that's easily integrable. That's going to be x cubed divided by 3. And again, we'll pick integration constant of 0. So, here we go with our ultraviolet voodoo. Ultraviolet is this main diagonal here, u times v. So u times v is going to be 1/3 x cubed. 1/3 x cubed, natural log squared. I'll go to that shortcut notation here. All right, so that's where we're at with uv. Minus the integral of v du. v du is the bottom row. Voodoo. So that's going to be the integral of all this. Let's get our constants together here. It looks like a 2 divided by 3. So we can pop that out in front. 2 divided by 3. And on the inside, it looks like one of the x's is going to cancel. So we're going to get an x squared ln x. Everybody agree with that?
Yes.
So we get that. That looks familiar. Yeah, that does look familiar. And I gotta stare at this for a minute. Something feels fishy. And I'm not sure what it's feeling fishy for.
The integral we're trying to do now, which we have to do a second time, is the same as what we just did.
It's identical to the one we just did, which is usually how we do, that's what we do with the one that Bryce, you showed me. It's one that I refer to as a twist. I feel like, did I
There's no
miss?
square though. On the LN.
Yeah, the first part, the V,
Yep.
it has a square, the U has a square instead of a knot.
Oh, that's what's getting simpler. Thank you.
The
Thank
LN's
you.
getting simpler.
Thank you. I was staring at him like it's
Oh.
identical, and the reason I was thinking it was identical is that yeah, that square right there. There's no square there. Yeah.
Yeah.
So we're going in the right direction. I don't know why I was looking at those saying they're identical. Those are not identical.
It's the same equation we just did on the other page.
On the other, that's where, right.
Yeah.
Yeah, that was the one we did on the other page. Yeah.
It's the exact.
Whew. Okay. So this is our assessment point. Is this integral easier? Yes, it's easier because this has a square and this does not have a square. That's our assessment point right there. It's like, oh yeah, it's easier. For whatever reason, I thought they were identical. And I was losing my mind. Okay, so that means that we most likely chose the best choices for our u and our dv because that integral is easier. But this integral still is not something that we can integrate immediately. We use integration by parts again. So we're going to use it a second time, and like was just pointed out, that was the integral we did earlier. So we're just going to, do that work again. And so we'll do a second integration by parts. We'll just write it right down below here. We're going to let u be natural log of x, and we're going to let dv be the largest part that's easily integrable. And now here actually there is a choice. And I want to point out kind of a strategy that could make our life a little easier. Our instinct is always to pull those constants out to the front immediately. And with integration by parts, remember that this whole integral right here is going to turn into a uv minus integral of v du. So that 2/3 is going to have to be distributed. So it's not a bad strategy to actually just leave the 2/3 on the inside. And then you don't have that 2/3 to distribute later. It doesn't matter. It's 6 of one, half dozen of the other, but.
Why is this x squared ln x, but you have ln x?
Why is DVX?
I haven't finished DV yet.
Okay.
DV, I was in the middle of writing when I started talking.
Oh, okay.
Yeah, I haven't finished. I was just pointing out, so I was pointing out here that I was about to say we're going to let dv be this, but then I wanted to point out that you could have left the 2/3 in there and chose your dv to be 2/3 x squared. You could have done that. So for us,
It distributes to the LN though too, right?
the 2/3?
Yeah.
Not to the ln because this is a product. It's not an addition.
Okay.
So if it was an addition, it would distribute to each of those terms. But
Gotcha.
here we have factors, not terms, because they're multiplied together, so it just sits in front. But we could leave it inside, and then we wouldn't have to distribute in the end. And then Zach, what was your did I answer your question?
Yeah.
Okay. So when we go to do our setup here, we just have to remember that, oh gosh, we have to distribute that 2/3. It's no big deal. And you have to have a little foresight to sort of see, oh gosh, why don't I just leave it inside? So you can leave it inside, you can move it outside, doesn't matter. All right, so now we have this 2/3, and it's got to be multiplied by, all right, so our second integration by parts, we're going to do UV, again, that's the main diagonal, and then we're going to subtract off the bottom row. So we are going to have 1/3 x cubed natural log of x minus the integral of voodoo, the bottom row, 1/x times x cubed over 3. Okay, x cancels with the numerator, so we get x cubed over 3. dx, close the bracket. So now we have that.
Go over that one more time.
Absolutely.
Would it be x squared over 3?
Yeah.
X squared over 3, yes, thank you. Yeah, I said it and didn't write it. Yeah, so we have an x cubed in the numerator right here, and an x in the denominator right there. So it should simplify to an x squared.
Because you're, okay, yep. you're good.
Because we're multiplying those two together. Those two get multiplied together for the VDU,
Yep.
so 1x cancels. All right, let's see if we can write this step with no typos. So the 2/3 distributes here, so we get minus 2/9 x cubed natural log of x, and then minus 2/3 times this, we can think of this as a minus 1/3, so that's going to be positive 2/9. And now let's integrate this x squared. We get x cubed over 3 when we integrate that, plus c. So this will be our antiderivative, and we could, the only thing we can do is combine this coefficient here and make this 2/27. So we could combine those two.
So when you integrate, you get x cubed.
X cubed over 3?
X squared divided by 3, so then it'd be x cubed.
X cubed
would there be
over-
another 3?
It would be x cubed over 9, but he already pulled the 1/3 out as a coefficient.
So we've got these coefficients. So those are going to be combined together to make the 2/9.
Ah, you already pulled it out.
Pull
Okay.
that out. Yeah, we could have just made it x cubed over 9 and then
Okay.
combined the denominators.
Thank you.
Yeah, combining.
Answers sure aren't pretty.
Is it plus 2/9 or minus 2/9?
Plus. Because we have two minuses in there, right?
Oh.
Oh, I know.
We have this minus right here that's distributing and capturing that minus. So that'll make it a positive.
Because it's all minus the integral,
It's minus that whole thing.
which then, when you do it a second time, alternates the sign.
Alternates the signs. So if you look in the book, there's a technique when you do repeated integration by parts called the tabular method, and they do it in the exercise. It's like one of the exercises that's down in the 50s or something. And there is a way, when you know you're going to do repeated integration by parts, you can just sort of set up one column here and one column here, and you do derivatives repeatedly and you do integrations repeatedly, and it gives you kind of a shorter method. It's not really emphasized that much anymore, but you can, there is another way to do repeated integration by parts. All right, so let's try this one. So now, we want to sort of, ideally, if we can see sort of why we're going to get a repeated integration by parts. So when we look here, we see that we have a polynomial factor and then a power on another function. And that power on the other function often is, if it's not just one, if it's a higher power, that's often going to indicate that we have to do integration by parts more than once. Now down here, we're going to see a similar type of thing where we are going to have to do integration by parts twice. And if you look, we have an x with a power other than 1, and the e, an exponential function, it's got a power, obviously it's not 1, it's got a variable in it. So this is going to be one of those things where we have two functions that have powers, then we're probably going to have to do repeated integration by parts. So let's go ahead and set up our integration by parts table here. So the u and the dv, so that's how we are going to parse the integrand. And when I'm looking at this, I'm seeing, okay, I see the x squared factor and I see the e to the 4x factor. The dx automatically is going to go here, has to go there. So there are more than two choices. You could be really, kind of nitpicky. But in general, it's going to be x squared or e to the 4x, one or the other. You could say, oh, well, can't we put the x with e to the 4x and then an x over here? You could do that, but that's going to be messy. So usually if you just look at your two factors, it's one or the other. And generally, you want to pick the biggest piece that's easily integrable. E to the 4x, I would say, is harder to integrate than x squared. So with that mentality, my first choice would be to put e to the 4x right here. All right, so the biggest piece that's easily integrable. And thinking sort of categorically, integrating an exponential is harder than integrating a polynomial. Polynomials are the easiest things to integrate. Also think of it this way. If you did choose to put your x squared there, wouldn't your powers of x be growing? Right? You'd end up with an x cubed over 3, which is going to end up making that integral that we get over here with the voodoo integral is going to make it harder. It's going to make it worse than the original. We don't want our powers of x to grow. So this is going to be a better choice. And that would be your first choice if you use the rule of thumb that we've talked about. So the biggest thing that's easily integrable. So then we differentiate. And remember, there's a dx there. And when we integrate here, we use reverse chain rule. So we get e to the 4x divided by 4. Integration, and we divide. All right, so then we do our ultraviolet voodoo. We're going to have 1/4 x squared e to the 4x. There's our ultraviolet. That's the UV. Minus the integral bottom row. So we have to multiply this stuff together now. Multiply those things together. There's a 2 in the numerator, a 4 in the denominator. So that's going to simplify to a 1/2. And this time, I'm going to leave it in here. This time, I'll do it differently than the other one. The other one, we pulled it out, but then we had to have those big brackets. So this time, I'm just going to leave it in. And then we have an x and an e to the 4x. Now, having some foresight, we know this integral is going to turn into a uv minus integral of v du. There's still that minus sign out front that does have to distribute across. So I'm going to do this to get rid of that. I'm going to say, let's pull the minus sign in also. We could do that. It's always easier when you're adding, because if you're adding, you don't have to distribute a +1. But if there's anything other than a +1, it would have to be distributed. So even just a minus sign, and distributing minuses tend to cause problems. So if we do that, this turns into a uv minus integral of v du, and there's nothing to distribute. So this actually is going to be the simplest way to not have to deal with any distribution. If you just force that to be a plus out in front by pulling that minus in. All right, let's just see how it works. Do you have to do that? No. We could do just what we did up here. As long as you're careful with your brackets. Totally fine. So let's see. So again, we're going to, another thing with repeated integration by parts, if you've chosen u originally to be the polynomial part, and you've chosen dv to be the exponential part, you want to stay consistent. You want to keep doing that. If now in the second integration by parts you switch them, you're going to go back to the previous integral. You're going to undo what you just did. So we want to be consistent and say, oh, we're going to let u be the polynomial part. So I'm going to let u be minus 1/2 x. And dv, we're going to be consistent and say, oh yeah, that's the exponential part again. And so then we take our derivative. We'll have du equals minus 1/2 dx. And we'll integrate over here. So we're going to get v equals e to the 4x divided by 4. We've got that. Yeah, these problems are not short. These problems are definitely not short.
I was working point about like the 18 like term long answer.
Yeah, you've got to be a good note taker here because it's very easy to get run off the page. So now you can see, since there's just a +1 out in front, we don't have to worry about signs. The signs just come out in the wash. So we multiply here. We're going to have -1/2 times 1/4. That's -1/8 multiplied by x and multiplied by e to the 4x. So there's the uv. And now minus the integral of v du. All right, so minus the integral. Again, we don't have to distribute a minus sign because we already took care of it. So minus the integral of v du. Now we look down here, and v du is negative. So if v du is negative, that's going to change this to a plus. And then we have 1/8 e to the 4x. 1/8 e to the 4x and dx.
How'd you get the -1/8?
So the -1/8 is coming from u times v. So if we multiply -1/2 times 1/4.
Okay.
So the 2's in the denominator, the 4's in the denominator, so we'll get a -1/8. And then once again, we're at the position where we have an integral that has an immediate antiderivative. So we are hot to trot. We'll use reverse chain rule. That exponent 4x is a linear expression. Anytime we have a linear expression, we use reverse chain rule. So we're going to divide by 4, which is going to give us 1/32 e to the 4x plus c. The integral of an exponential is itself divided by the derivative of the exponent. All right, any snag there you want to talk about?
I can see how adding the -1/2 inside the integral makes it a little bit simpler, because then you can forget to cross it back over to both.
Yes, very easy. It is the most common mistake grading this exam of all, is not distributing this constant properly. You're just forgetting to put these big brackets and just keep putting it on this one and not on both. So it's something you have to remember to do, but if you can remember to just make this a +1 out in front, it actually simplifies it a bit. You don't have to deal with big brackets. Let's try one with limits of integration, so a definite integral. Yay, baby. And again, we have a natural log here. So first off, let's just set up our generic setup, dv and u. And this is not a traditional integration by parts because we only have one factor. Normally we think of integration by parts as undoing a product. Well, it can also be used for natural logs and inverse trig functions. So we are going to instantly choose the natural log has to go over here with the u because if we put it over here, we'd be doing the same problem. We'd be trying to integrate natural log of 2x, which is what we're trying to do. So we put it over with the u. And then we differentiate. So du equals, what is the derivative of natural log of 2x?
2 over x.
Nope.
1 over 2x times 2.
1 over x.
Yes.
Yeah, 1 over x.
So it's-
over 2x.
It's
yeah.
1 over 2x multiplied by the derivative of 2x. So it's 1 over 2x times 2, which ends up being 1 over x.
Right.
You see it? So it's 1 over 2x multiplied by 2. So when push comes to shove, we still end up with just 1 over x.
And where is it?
Question, Dustin?
How do you know it's not natural log of 2 times x? How do you know that's like a 2x? They would write it x natural log of 2?
Exactly.
Okay.
And that's why we usually write things in this particular order. Like when we look at sort of the traditional way to write expressions that have natural logs, we usually put the natural log at the right side so that there's no confusion. Like if I put this natural log squared of x out in front, then you're sort of saying, well, is the 1/3 part of that? So usually we write it at the right-hand side just to kind of make that a little clearer.
Okay.
What we should do and don't do is wrap it all in parentheses,
Yeah.
right? That would be the smartest thing to do, but they want to eliminate as many type strokes as possible.
Also, generally a good idea to assume that it's the harder one, because they wouldn't give like
Yes,
the
exactly.
option of a constant times x. for
Because then the natural log of 2 is just going to factor out to the front. Yeah, assume the worst case scenario.
Hey, why is it multiplying by 2? Are you supposed to like divide?
So that's the chain rule. When you differentiate a function,
Are you doing a derivative or antiderivative?
here we're doing a derivative.
Oh,
Here we're doing a derivative. So the derivative of natural log is 1 over the inside multiplied by the derivative of the inside.
okay. So I thought it was an integral.
This side is integration.
Okay.
This side is derivative. So here we integrate dv and get v. We integrate dx and get x. So we've got that. All right, so now we do the ultraviolet voodoo. Ultraviolet voodoo. So yeah, so here this is what you're referring to, Dustin. We're going to put that x out in front. We wouldn't want to write it as natural log of 2x times x.
Okay, got it.
So we do it that way, uv minus the integral of v du. Ooh, doesn't that just become dx?
It does.
All right, because this x is in the numerator, this x is in the denominator, so those two x's, these are both canceling.
So
Do we keep just the same,
Oh, in the limits of integration.
that's integration.
So here's how we technically are going to write that. We are going to put an evaluation stroke here, 1 in E and a 1 in an E. And you have a choice. You could evaluate this right now, but usually it's just better to wait till the end because the limits of integration are the same on both pieces. So it's being patient and just integrating and evaluating at the very end is what I would recommend. So let's do the final integration here. So we're going to get minus x. This is going to go 1 to e for the whole thing now. So this evaluation, 1 to e on this antiderivative out there, it's going to be the same limits of integration for this antiderivative, so we can just do it all at once. We do need to write this in here, though, because it has to be understood that this does get evaluated at those endpoints.
So you need both of those, right?
Yes.
Evaluate that and then integrate.
Yeah, so we have to evaluate it at 1 and e, so we have to have this green line, but then we also want to have those up there as well.
Okay.
But then once we do that second integration, these limits of integration carry for all of the entire antiderivative. So plugging in e, we're going to get e natural log of 2e minus e And then we subtract off antiderivative at 1, so that's going to be 1 times natural log of 2, and we're subtracting. So natural log of 2, and then we're subtracting a negative, so it's going to be plus 1. And this could be simplified a little bit. I'd be totally fine with that answer right there. You could say, okay, done. The book and the MyMathLab homework is probably going to keep going though. So you could rewrite this. How do you rewrite the natural log of a product?
You do ln 2e minus 1.
Or it's ln of 2 plus ln of e?
Yes.
Yeah.
So ln of 2 plus ln of e. That is how you could rewrite natural log of 2e. Do we agree? So we have those rules of logarithms. We have the quotient one, which says the log of a over b is the log of a minus the log of b. And then we have that the log of a product is log of a plus log of b. So we're using that.
But you're pulling out the e, right?
So we're treating this as 2 times e. Now that can be further simplified.
So then you, okay, so but what about the minus e?
Yeah, we're
Oh, okay.
we're getting there. So then we have the minus e, the minus ln2, and the plus 1. Okay, and then natural log of e is 1. So this is going to become, and let's distribute. So we have e natural log of 2 plus e minus natural log of 2 plus 1. And so when all is said and done, we have e ln2 minus ln2 plus 1. So that would be our simplified answer.
When you distribute the e to the ln e, you get just e.
Because ln of e is 1.
Ah, thank you.
So this part, yeah, the value of this right here is 1. So then we have e times 1. But I would not be that nitpicky. If you got to this point, I would take that. Okay, now we got a really gnarly looking one. Again, though, if we just sort of think about it as a product of 2 functions, we have the y function and we have the inverse tangent of y squared. So that y squared, again, Dustin's point, it would be a lot neater if we just always wrapped up stuff inside functions, but we don't. So there is some context. Okay, so once again, we're saying, okay, well, there's really just 2 factors. There's the y and there's the inverse tangent. So one of them's going to go with u and one of them's going to go with dv. We want to put the one with dv that's easily integrable. Well, we don't know how to integrate inverse tangent off the top of our head, so that's going to go with the u. So here's how we'll set it up. So we're going to put u equals inverse tangent of y squared. And then dv is everything else, so that's just y dy. So there's our subdivision. That's the one that makes the most sense. We don't know how to integrate inverse tangent, so we'll throw it with the u because we can differentiate anything. We can differentiate anything.
Jim, this kind of answers my question too, because they put the y to the left.
Yes.
Like if they put the y to the right, you wouldn't know what.
Then it's ambiguous.
Yeah.
Right, exactly. Yeah, they're always going to sort of order it that way to make the, hopefully to make it so that it's unique and there's only one way to interpret it. All right, derivative of arctangent. The derivative of arctangent, if it was just arctangent of y, that would be one thing, but it's the arctangent of a function. So if it's just arctan of y, the derivative is 1 over 1 plus y squared. But if this is not, if that's more than just a variable, we then have to use the chain rule. So,
You multiply like 2y?
exactly. So du, exactly. So we get 1 over 1 plus y to what power? Y to the 4th power, multiplied by 2y in the numerator. Super important, because if we don't get that derivative right, when it becomes part of the next integral, we're hosed. Right? This part, the bottom row, becomes the next integral. So if we get that derivative wrong, then when we set up the integral of the voodoo, then we're hosed. We've got to make sure we understand chain rule really well. So derivative of arctan, 1 over 1 plus the variable squared. More generally, 1 over 1 plus the inside squared. But then we have to differentiate by the inside.
So then you times it by, so you do the chain rule all the way out.
Chain rule. So if this was, let's suppose this was arctan of y cubed, then this would be 1 over 1 plus y to the 6 multiplied by
3y.
Y squared.
3y squared.
What if it was like x, tangent, arctangent of like x squared minus x plus 3?
So if it was arctan of x, you said x squared?
Yes,
X squared minus x plus 3?
yes.
So if we're going to take that derivative, we're going to have 1 over 1 plus the inside squared, so you'd have to FOIL this whole mess out, and then multiply by 2x minus 1 up top. So 1 over 1 plus the inside squared, and then the derivative of whatever's sitting inside that function, inside that arctan. Everyone okay with that?
Yeah.
Zach, you okay with that? Makes sense. Okay, so then here we integrate. So we're going to have that v is equal to y squared over 2. And our ultraviolet voodoo, so uv is the main diagonal. So we have 1/2 y squared. So that's this part, multiplied by inverse tangent of y squared. So there's uv, minus the integral of v du. Okay, so v du, notice that this 2 is in the numerator, this 2 is in the denominator. So when we multiply those together, those 2's are going to cancel each other out. So we are going to end up with, do we agree on y cubed divided by 1 plus y to the 4th?
Yes.
And then the bar for the definite.
And then the bar for the definite. So let's put that in both places. So we're going to have a bar here from 0 to 1 over root 2. And then we're going to have limits of integration over here, 0 to 1 over root 2. And then what form is that integral in? That's log-ish. It's log-ish. The derivative of that denominator is what?
4y cubed.
4y cubed, so let's massage, put a 4 up there. But if we put a 4 up there, we need to put a 4 down below out in front to offset it. So now it's in log form. The denominator's derivative is 4y cubed. We have a 4y cubed up in the top, so that we can integrate immediately. We do not want to evaluate this yet. We're going to evaluate all at once together because the limits of integration are going to be the same for both antiderivatives. So this will be -1/4 coefficient And we're in log form, so now we get natural log of the absolute value of the denominator. Well, that denominator can never be negative, so we don't need the absolute value. And then our evaluation is on this interval. All right, any issues getting to that point?
How are you recognizing it's in log form again? Because it's
When the denominator's derivative is in the numerator.
Practice.
Practice, yeah. So anytime we have a polynomial in both top and bottom, you want to be thinking, oh, is the polynomial up top 1 degree less? Right? When you differentiate a polynomial, you ratchet down the power by 1. So if the power up top is 1 less, then it's a good chance that you're in log form or close to it. Log form. Log form will, we will see that ad nauseum this semester. Log form. Okay, log form. Love it. So now we're going to plug in the upper limit of integration. Does the lower limit of integration give us anything?
It gives you an ln of 1, right?
And what's ln of 1?
Yeah, it's 0.
0. So when 0 is plugged in here, we end up with ln1, which is 0, so this is gone. When we plug in 0 here, we get 0 times something. Also, inverse tangent of 0 is 0. So this 0 is not contributing to the evaluation, so we don't have to worry about plugging that in. So let's plug in the 1 over root 2. 1 over root 2 squared is 1/2. And then we have arctangent of y squared, which is arctangent of 1/2. So that 1 over root 2 is getting plugged in there, and we're squaring it and getting a 1/2. And then minus 1/4 natural log. Let's see, 1 over root 2 times 1 over root 2 is 1/2, and then we do that again, so we get 1/4. So we're going to have 1 plus 1/4, which is 5/4. Can inverse tangent of 1/2 be simplified? Inverse tangent of 1/2, what you should be saying in your mind is angle on the right side of the unit circle with a tangent value of 1/2. And that is not something that we know. When we look at tangent values, remember also that tangent values mean slope. Do we have a terminal ray on the right-hand side of the unit circle with a slope of 1/2? No. We have these three on the right half of the unit circle. This one in the middle has slope of 1, right, at pi over 4. Slope is 1. Inverse tangent of 1 is pi over 4. The slope of this one is root 3 over 3. Inverse tangent of root 3 over 3 is pi over 6. And the slope of this one up here is root 3. So inverse tangent of root 3 is pi over 3. So when we look at an inverse tan is an angle that's on the right side of the unit circle. It is the angle on the right side that has a tangent value of 1/2.
Which is
We don't know. It's some
somewhere between.
irrational angle. It's somewhere in between. So the slope here is 1, so it's somewhere down here where the slope, that thing right there has a slope a little bit more than 1, right? Root 3 is like 1.7-ish. So, so we're talking about an angle that's down here below this somewhere. Don't know it.
Because that's equivalent to 1 over root 3, which is a bit less than 1 over 2, so it's between those two angles a little bit somewhere.
Yeah, you could think of it that way. Yep.
Somewhere in the middle.
Somewhere in there.
Doesn't matter, because we don't have a number for it.
Yeah, so this one is not a special angle. So it just stays. It's not a special angle. Random angles are generally not special.
Usually.
If it was sine and cosine, you can do 1/2.
That's right. If it was inverse sine of 1/2, what would it be? Inverse sine of 1/2, we would say to ourselves, angle on the right that has a sine value of 1/2. Sine is the y-coordinate, so that would be pi over 6. And if it said inverse cosine of 1/2, we would say angle on the top with a cosine, i.e. x, of 1/2, which would be pi over 3. Yeah, so practice your unit circle, because your unit circle is going to be around all semester.
By the way, it's 0.46.
Your unit circle. Okay.
Right, 463.
So there is our lovely antiderivative. Question?
That is definitely
Is the part of math where they stop giving you things that all cancel out.
Yeah. Yeah, we are juggling. We are juggling. It doesn't, all the balls, the balls are staying in the air. The balls stay in the air in Calc 2. I will do a volume. So this is a solid revolution. We're going to rotate around the x-axis on this interval that starts at 0, ends at pi. So we're going to create an egg. When this thing rotates around the x-axis, we're going to get some sort of funky egg thing.
a pointy egg.
A funky egg
Very pointy.
So shell?
with pointy. I would definitely not use shells here.
Yeah.
Let's take you up on that, Bryce. Let's say, yeah, let's use shells because we are so masochistic. Right? So if you were going to use a shell, your element would have to be parallel to your axis of rotation. So then you would have to be able to identify this curve and this curve. These curves would have to be, separate.
So you'd have to subtract the curve from itself.
Yes. So you would have to solve this for x, and so x would equal the inverse sine of whatever this angle is over here.
Oh.
It would be a pain in the neck.
Arc sine.
You'd have an arc sine and an arc sine and an arc sine and a shifted arc sine. Yeah. So do you see why that would be really hard? So this function, isn't this function presented as it's presented as a y value, right? This is presented as a y value, so it's measuring height. So it's going to make more sense to go like this, and that's going to end up being the radius of the disk. Right? So when that vertical element rotates around the x-axis, it's going to create a disk. And the radius of that disk is that vertical distance, it's that y value, which is how the function is presented, which is going to be the easiest way to get at this, for sure. Now, we could also use symmetry, and if you were really dead set on using shells, we would probably parse it in half and go like that. If you really wanted to, so that you didn't have to use a shifted inverse sine, you could just use one inverse sine, but then you'd be integrating an inverse sine, which would be still is going to be messy regardless. So whenever you can use disks is the easiest way. If you can use a disk. So what is the area of a disk?
Pi r squared.
Pi r squared. So we have the area of a disk. So in general, we've got pi r squared. And this disk we're imagining right here, right? It's coming out of the board right at you, looking like that. And the radius of that disk is the function. And the function is sine of x. So it's pi times the sine squared of x. So that tells us the area of the disk at x. And if we wanted to double check that we have the right function, we could say, well, what is the area of the disk at these two extremities? What would the disk be when we rotate around the x-axis on those two tips? We get an area of 0. And so if we plug in an x value of 0 or an x value of pi, this area function should predict 0. And sure enough, sine of 0 is 0, sine of pi is 0. So that is, most likely we're on track. Success. And then we know that volume is the integral. We could use symmetry here, but we don't need to because we already have a 0 as the limit of integration. So using symmetry, we could go 0 to pi over 2 and double it. Not a lot to be gained with symmetry here. Usually we use symmetry to introduce a 0. If we can somehow use a 0 that's not there, here it doesn't matter. So we'll just go 0 to pi. And then we integrate the area function. So we're going to integrate that.
Power shifting?
Well, I just realized something. What axis does it say to rotate around?
X-axis?
Why?
The y-axis.
Yeah.
I think
One of those days.
We are in the integration
And
by.
it's revolved around the the y-axis. It's bounded by the x-axis, revolved around the y.
What a-
No. So yes.
So I just went back up to what section are we in? Integration by parts. That integral is not done by integration by parts, which is why I sort of thought something's wrong. Okay, so
It's just because we're doing
It's
it wrong.
too easy.
it's too easy. Sorry about that. We have to read all the words,
That's so sad. I hate that.
right?
Wait, this isn't English.
And it's like when I was in English classes, I only read the even pages, and that just always seemed to be enough. And so I'm still in that habit of not reading all the words. My wife, being an English teacher, hates the fact that I don't read more. So, we are rotating around the y-axis.
Like for a story, it doesn't work. For like art, maybe.
So we're rotating around the y-axis. And if we rotate around the y-axis, no matter what, so when we chose that vertical element, the idea in choosing that vertical element is that this region is vertically simple. Whether we're going around x or going around y, we'd rather draw a vertical element because that horizontal element it's got the same curve on the right and the left, which is a pain in the neck. We never really want the same curve as the right and the left endpoint. So we still want a vertical element. That's the correct element, regardless of what axis we're going around. Now, if we're going around the y-axis, this does create a shell now, because we are now parallel to our axis of rotation. So the area of our shell is going to be 2 pi times the radius times the height. So this is now the height. And can you tell me what the radius is?
X.
Yeah, the radius is x. So the radius is x. Okay, so the area of our shell is 2 pi x sine x. That looks more integration by parts-ish. So the height is sine x. The radius is the distance from the axis of rotation over to your representative element. Your representative element or your representative rectangle is sitting there at x. So the radius is given by x. So now our integration will be from 0 to pi. Again, we could use symmetry, but we don't need to. Oh, actually, we don't want to use symmetry here for the shell method. That won't work, actually. Does everyone agree that symmetry would not be an option here with the shell method? Do you see why it's not an option? Yeah. Right. If you look at the right half of this generating region, that's going to be moving on a wider radius. It's not creating a symmetric volume. If it was going around the x-axis, it would create a symmetric volume, but around the y-axis, it's not creating a symmetric volume. So we don't even have the option.
Could you use a washer method on it too?
We could use the washer method, but again, if we did use washer, we'd be in that dilemma that we'd have to use a horizontal element using the same curve as the left and right boundary.
Okay.
That would be difficult.
And your curve is arc sine of x, which is a lot less pretty than sine of x.
Arc sine of x is a lot less pretty, and then arc sine of x plus a shifted arc sine of x would be, I'd be impressed if you could make it all the way through that integration. Okay, so here we have an integration by parts. Now, another one of those situations where you might say, oh, let's just factor out the 2 pi. Well, if you factor out the 2 pi, you're going to have your ultraviolet voodoo when then the 2 pi has to be distributed across. It's just easier to leave the constant inside. It will be easier. So if we just leave it inside, I'm going to think of this as 2 functions. And we have to pick a u and we have to pick a dv. And when we focus on dv, we say to ourselves, let's pick the biggest part that's easily integrable. And by biggest, maybe I should use the word more complex. The most complex part that is easily integrable. Integrating x is easy. Integrating sine x is also easy, but it's more complex than integrating x. So we want to integrate the more complex one. So we're going to put sine of x over here. We're going to put 2 pi x over here. And when we differentiate 2 pi x, we just get 2 pi dx. And when we integrate over here, we get minus cosine. So how does that little integration by parts table look? Does that look right to you? Everyone see how the derivative is just the constant in front of the x. Integrating sine is negative cosine. And now we can go with our ultraviolet voodoo. So we're going to get negative 2 pi x cosine x. There's uv. So uv minus the integral of v dx, v du, voodoo, v du. But notice that v du is negative. So we're going to get plus integral 2 pi cosine x. And then we put in our limits of integration. And we said we're going from 0 to pi. So both of these have 0 to pi's. And we'll finish off the integration and evaluate everything in one fell swoop. What's the integral of cosine? Integral of cosine is sine. 0 to pi. And then we go to evaluate this and notice that this term, sine of pi is 0, sine of 0 is 0. 0 and pi are at the sides of the unit circle. They both have y values of 0. Sine is the y value. So that term doesn't contribute at all. And if we plug in 0 right here, we get 0. So we really, it all boils down to just plugging in pi. And we get this. Cosine of pi, negative 1. So we're going to end up with 2 pi squared. That will be the volume.
Good job, Reese. I got negative. I forgot that negative one was pi. Bad job.
When you end up with a negative volume, you've got to be pretty concerned about what you're
Yeah, if you have a negative volume, double check your signs. Because something must be wrong. Yeah, you should get a positive volume. Always.
All
You get the new stuff right.
All right, let's take a 10-minute break. 10-minute break, and then we will do integration by parts with a twist.
with a twist.
With a twist.
I know what that is.
Integration by parts with a twist.
What did the negative? It's cosine of negative and it's negative 2 pi.
Oh, right. Oh. Okay, so now we are going to do the ultimate integration by parts, which I refer to as integration by parts with a twist. And so I'd like to distinguish it with this name, integration by parts with a twist, just because there is a totally different nature to it. So this is the one that you were talking about, Bryce. And notice when we do our integration by parts, we set up our table and we have our u and we have our dv. And we know that the dx goes with the dv. So we have that set up. And we usually are saying to ourselves, let's pick the more complex function to put with the dv. And what you're going to notice here, if you think about it, both the trig function and the exponential are going to be spinning through their derivatives, right? E to the x stays e to the x. No matter how many times you differentiate it or integrate it, it stays e to the x. Sine is going to be bouncing sine, cosine, sine, cosine, sine, cosine, sine, cosine. So there's not going to be one of these functions that's going to sort of collapse. Like when we had the x squared out in front, it went from x squared. If we differentiated, it went down to x. If we differentiated again, it went down to a constant. So both of these functions are circular in nature when thinking about derivatives and integrals. If you put the trig function over with the integral, same thing. It's going to integrate cosine sine, cosine sine, cosine sine. So they're both circular in nature with the derivative and integral. So that's going to be what distinguishes it with the twist. All right, so here's what's going to happen. So let's try this. So if you know ahead of time that this is integration by parts with a twist, you'll come to learn that it doesn't matter which one you put with u and which one you put with dv. It doesn't matter. I'll just write it in order. I'll put the exponential here, and I'll put the trig function here. But it does not matter.
Are we gonna know that it's with the twist in the exams?
If you study.
I can't remember if I said with a twist. I might have given you that hint. Well, you can look at the previous test and know for sure. I just can't remember off the top of my head.
You know, because it's an E in the.
Yeah, it's always with an e, a sine, or an e and a
So
cosine.
if it's two cyclic functions.
If it's two cyclic functions, it's going to be,
It's gonna be twist.
yeah. And by cyclic, we mean the derivatives are repeating. Okay, so let's find the du. So du is going to be, let's see, derivative of an exponential is itself multiplied by the derivative of the exponent. Integration, the integration of sine minus cosine, integral of sine is minus cosine of the same angle, but then we have to divide by the derivative of the angle. So we had to use chain rule on the left and reverse chain rule on the right. Okay, now, knowing what's going to happen, I'm going to choose to call this integral something shortcutted. I need a symbol to represent that integral. Usually we can just sort of go systematically across, but you're going to see that there's some clever algebra that we're going to need. So we need to call this integral something. The books are all going to call it I. A few years ago I had a student that said, let's not use I, let's use something more creative. So we got in the habit of using omega, and I haven't gotten out of the habit. You can use whatever symbol you want. Zeta, eta, beta, neta, whatever. Does not matter. I am going to use that symbol, capital omega. So that's just representing the integral. And so I just need to be able to rewrite that whole original integral as one symbol. So I'm going to call it omega. And omega is going to be u times v. So we're going to do our standard stuff. So that's going to be minus 1/3. And then usually we put the exponential before the trig function because we don't want that sort of bleeding into the trig function's angle. So we have that. So that's the typical way. Constant, exponential, trig. So there's our uv. And then we're going to subtract off the integral of the bottom row, the voodoo. Notice that the bottom row multiplies to a positive.
Where did the -2 go?
The -2.
Oh, I'm sorry.
Oh yeah, we haven't gotten there. That's where we are right now.
Yeah.
So we did the diagonal first, so we did those two. Now we're going to subtract off those two. And does everybody agree that v to u is positive here? Right, those are two negatives, so they just cancel. So we're going to get, we're going to subtract off all this, and that's a plus on the inside. And then we can choose to put the minus in here if we want. So we'll get to that in 1 sec. So we're going to have this as our integral. And if you compare it to the original, it's of the same difficulty. Same difficulty. It's not easier, it's not harder. It's just trig function times e. Now, we're going to do integration by parts again. And here's where I am going to say, let's be a little clever. Let's turn this into a plus, and let's put the minus sign in there. So let's do it that way. Because we don't want to draw the big brackets and distribute. It'll be a little bit simpler. So we're going to use integration by parts again. Now, the second iteration of integration by parts, again, you want to use the same pattern you established above. So if u was your exponential, it should remain your exponential. If you did it the other way, no problem, but just be consistent. So I'm going to choose this whole thing right here as the, come on, stay blue. So we're going to have, we have these two functions. I'm going to put the negative 2/3 e to the negative 2x with the u. And then for dv, we're going to pick the trig function. So there's our setup. All right, so let's go ahead and take the derivative here. So the derivative of an exponential is itself multiplied by the derivative of the exponent. So we have to multiply by -2. So that's going to give us 4/3 e, bless you, to the negative 2x. Integrating cosine is sine divided by the derivative of the angle. Okay, so that is where we's at. Any questions on that second integration by parts? I'm just going to rewrite what we already have above. So we push that minus in, which is going to make our lives a little simpler here. We've got plus. Now it's u times v, which is going to be -2/9, -2/9 e to the negative 2x times sine of 3x. So there's uv minus the integral of v du. So that's 4/9 e to the minus 2x times sine of 3x. Let's make sure we all agree and see that as our result. Does everyone agree with that? So u times v is the main diagonal, v du is the bottom row, and we're just adding. So we add this multiplication, which happens to be negative, so -2/9. And then we subtract off the bottom row. Well, the bottom row is positive, so the minus sign is preserved. So the left side of this is this omega that's representing the original integral. And do you see what we have out in that new integral? What do we have? How does the new integral compare to the original?
We have omega.
Same with the constant.
Right? So if we call the original integral omega, the integral on the right is just -4/9 times omega. Omega is the integral of e to the negative 2x sine 3x. So this is just a constant multiplier of the original. And now we're in algebra 1. We have a linear equation in omega. How do you solve a linear equation in omega? you combine the omegas. So we add 4/9 omega to both sides. On this side, we think of this as 9/9 omega. So we're just going to collect like terms. Just algebra 1, collect like terms. So we have 4/9 omega plus 9/9 omega. How many nines does that give us? 13/9 omega on the left. Now, on the right, we know that this omega is representing an indefinite integral. And if it's representing an indefinite integral, we know that there are going to be a family of antiderivatives. And when this omega is over here, there's that built-in plus c. As soon as we do this twist, where we twist this omega over to the other side and combine it, then we need to drop in a plus c. Because this omega represents an indefinite integral, which is a family of antiderivatives. So as soon as we twist those omegas together, we need to have that plus c on the right-hand side. And we are a stone's throw away from completing it. What is the very last step for this Algebra 1 problem? We just want to isolate omega. We want 1 omega. The goal is to solve for 1 omega. We want to know what omega is equal to, so we multiply both sides by 9/13. So therefore, omega is equal to, if we multiply both sides by 9/16, 9/13, thank you. We're going to multiply both sides by 9/13. So this is going to be 9/39.
Or 3/13.
Oh yeah, there's a common factor of 3. Thank you. It seemed like there was a lot of...
Yeah. A little bit easier to write.
Yeah, let's cancel a 3. So if we multiply by 9/13, we end up with 3, negative 3/13. And we've got the e, the cosine. All right, and then 9/13 here. Oh, the 9's cancel, so we get 2/13. And now this constant over here is like a recycle bin. A constant times a constant's just a constant, we don't care. Clearly this c is different than that c, but it doesn't matter. If we were to isolate and solve for c for some particular antiderivative, we would be using this one down here. Doesn't matter that those two c's are different. As soon as we get to that new line, we never go back to the old line, so we can just use the same letter. Constant times constant. Oh. Okay. Very. All right, so there's our antiderivative. So you all tried this one, e to the x cosine. I've taken out all the constants, so it's just the trig function with a single angle, the exponential with a single exponent. So see if you can do the twist with just that problem where it's reduced just down to the bare bones. No weird coefficients. So we know it's going to be a twist because both functions have circular derivatives. Choose whatever creative letter you want. If you don't want to use omega, use something else. Try to parallel what we just did.
So flip it.
So you're going to add it to the left. This is going to be 25 over 25.
Oh, so 25 over 25i, or 25
Yes.
over 25 omega.
Yep. Plus the other one, now that'll give you your new coefficient of that integral.
Plus 16 over 25. Give us 9 over 25. No, it's plus?
Yeah, you're adding.
Okay.
So it's going to get bigger.
then you just plug it back into the original equation.
Well, you don't have to plug anything back in, you just have to divide by the coefficient. Right, as soon as we added it to the left-hand side,
So we're gonna have to write like this.
so now the right-hand side is this plus constant, which you have, so now we just multiply this side by 25 over 41.
This side,
Yep.
not that.
That's
Okay.
gone though, because you moved it to the left.
Gotcha.
Go on.
Do that right? Probably not. It's done.
All right, were you able to do the twist?
Or you actually divide by 2 times parentheses sin x plus cos x. And then you got it in the back of the x divide by 2 times. But it doesn't really matter.
So when you're doing the twist, again, it doesn't matter what you put where. I'm just going to do it in order. So we have the two functions. There's our integration by parts table. I'm going to call this integral omega, call it whatever you want. So the original integral will be uv, which is e to the x times sine x. uv minus the integral of v du. So that's where we're at.
Someone brought the dx down on the v, right? It should just be sine of x, not sine of x.
Yes, there's no dx there. Thank you.
So you don't have a dx squared.
No dx squared. Ugh. That is advanced calculus. When you start getting into combining differentials, when you do algebra of differentials, you have that to look forward to. Okay, so now we want to do the same thing. Now, if we want to be clever, we could say, ooh, let's push this minus sign inside just to simplify our parenthetical situation later. So we'll let u be negative e to the x, and let dv equal sine of x dx. Bless you. Derivative is going to be itself times dx. And then when we integrate, we're going to have negative cosine. So now we have e to the x sine x. All right, so u times v, that's positive. So it's plus e to the x cos x. uv minus the integral of v du, that's the bottom row, that's cosine x dx, that's cosine of x. Oops, I put them out of order, doesn't matter. I'll put a dot. So it matches the original. So our next line, we're going to add that. We're going to twist those two together. So this is just minus omega. So we're going to end up with this. So we add it to the left-hand side. And as soon as we add it to the left side, we introduce a constant of integration on the right. So this whole piece right here This is omega.
Constants included in indefinite integral.
So that is omega. Add it to the left side, we have omega plus omega, it's 2 omega.
So the integration is part of that equaling omega?
Mm-hmm.
So omega is the
That's
integral.
what I meant.
Omega is the integral, so it's got that built-in plus c with it. So we've got to make sure that when we eventually solve for omega, there has to be a plus c. And so here will be the final answer. And once again, the constant acts like a recycle bin. If you multiply it by a constant, you just get another constant. So there is how you do integration by parts with a twist. Pretty cool. Pretty cool that it works. So if you were blindly doing integration by parts, this is where you notice something. When you get to this new integral, if it's easier, you're definitely on track. If it's harder, go back and start over. If it's of the same degree of difficulty, you're probably in this integration by parts with a twist setup.
What if it is like the integral, like it's like infinite series?
There'll always be a point where it loops back on itself. For any
Did you just say infinite series?
Yeah.
Have we done infinite series yet?
No.
No, I'm saying like, is it possible for an integrand to be an infinite series?
Like for it to keep.
Is it possible for an integrand to be an infinite series? So are you asking, is it possible to integrate an infinite series?
No, for it to be never repeat itself kind of thing, I think.
I'm not sure. You can integrate an infinite series. We will do that. But we're not going to see this as being an infinite series, but maybe what Lincoln is saying is more what you were asking? You said an infinite series.
Yeah, like if we take the integral of a thing, it becomes infinite series.
Well, we're only integrating common functions, so we don't need to represent them as infinite series.
Okay.
But it's possible to integrate an infinite series. An infinite series is going to, for us, will turn out to be an infinite polynomial. And a polynomial you can just integrate term by term. So we will get to that though.
It takes forever.
If you do it term by term, it's going to take forever. I wouldn't recommend doing it that way though. If you integrate term by term, it's going to take so long. Okay. 8.3, section 8.3, we want to be able to integrate products of trigonometric functions, ideally without integration by parts. So when you see a product, you know, you can see both of these as products, it's true that you could probably go to integration by parts. You could go to integration by parts. But there's a better way if you have products of sines and cosines and products of secants and tangents. So first we're going to start with products of sines and cosines. And here is our strategy. So powers of sines and cosines. And now in this first one we don't have any cosines. But here is our strategy. If one of the powers is odd, split off a factor for the differential and convert the leftovers. Okay, what does that mean? This is what that means. So when I look in here, I see an odd power, split off one factor for the differential, so I'm going to pull off one factor of sine, and I'm going to sort of think of it as hanging out with the differential. So what's left is sine squared. Bless you. So if we factor off the one factor, this is what I'm referring to as the leftovers. Okay. Factor off, convert the leftovers. What does convert the leftovers mean? So we either have an integral with sines and cosines, and if our leftovers are sines, we convert them to cosines. If our leftovers are cosines, we convert them to sines. Okay, so that's what we're going to mean. So the sine squareds are leftovers. Notice it's got an even power. If you start with an odd power and you pull one off, you're going to be left with an even power. So you can always use a Pythagorean substitution. When we get to secants and tangents, it's the same idea. If the leftovers are secants, we turn them to tangents. If the leftovers are tangents, we turn them to secants. So when we say convert the leftovers, sine to cosine, cosine to sine, secant to tangent, tangent to secant. All right, so let's convert these leftovers now. So sine squared is the same as 1 minus cosine squared. So now we've converted the leftovers. So once we've done that, now we're ready for u sub. So pull one off, convert the leftovers, now we use u sub. What are we going to let u equal?
1 minus cosine squared x?
No.
Sine of x.
Because if we took the derivative of that, if we have cosine squared, the derivative's a, right? Bring down the 2, subtract 1, take the derivative of cosine. It's way simpler. We just let u be
Cosine?
cosine.
Oh.
If we let u be cosine, so if we let u be cosine, then du grabs that sine of x that we threw over to the differential. So the derivative of cosine is minus sine x dx. And so let's watch how this substitution unravels really nicely. So this will become 1 minus u squared. And then sine x dx is minus du, so we'll put a minus out in front and then a du. And then we can integrate. And then we distribute the minus and back substitute. So we're going to end up with minus cosine of x plus 1/3 cosine cubed of x plus c. So the u is always going to be just sine or cosine or secant or tangent. It's going to be simple. It's not going to be as complex as like letting it be a square or something. All right, any piece of that you want to ask about?
Yeah, is that a negative before the integral?
Yes, that blob is a negative. Yes. Yeah, it's funny. Sometimes this it sort of wants to take the pressure, I think, and make it thicker. I can't quite tell. Okay, so here's one that has both sines and cosines. And so the rule says if you've got a product of powers of sine and cosine, if one of them has an odd power, pull one factor off, creating leftovers that have an even power, and then convert the leftovers to the other function. So let's go. So here we see, oh, okay, cosine's got an odd power. So we're just going to let the sines linger. We're going to pull off one cosine, feed it to the differential. So we're sort of thinking about grouping the cosine with the differential. What do you think we're going to end up letting u equal? Sine, so that when we take sine's derivative, it grabs that factor that we grouped with the differential. But before we get to that, we have to convert the leftovers. So these guys right here, these are the leftovers. So the leftovers are the ones that were left behind. We took one away. Those are the leftovers. We want to convert those to sines. We know that cosine squared is 1 minus sine squared. So that's where we're going. So Pythagorean theorem, 1 minus sine squared. But we have to square it. So now the leftovers have been converted. Cosine squared is 1 minus sine squared. We've got 2 cosine squareds, so we have to square that. Now we're ready to rumble. So we say, okay, let's let u be sine of x. We're always going to let u be the other trig function, because its derivative will then grab the cosine. So du will be cosine of x dx. That's going to simplify this tremendously. We're going to have u squared times 1 minus u squared squared du. All right, any questions up to that point? The rest is just basic algebra. So that's the heart of it is done. Now we have to do our algebra. We have to be able to FOIL. So we get u to the 4th minus 2u squared plus 1 du. And then we distribute. So when the algebra is done, we have that.
Integrate.
And now that's easily integrable, and then we just have to back substitute. So,
Sine to the 7/7.
sine to the 7/7. Yeah, we could do it all at once. Let's not do it all at once. We could, and you definitely probably will on the test. So we integrate, and then we plug in a sign. So, looking at that, is there anything you're not sure about?
If both of them have an odd exponent, is there a rule for that?
Pick whatever one you want.
Okay.
Usually, since you have to convert leftovers, usually you'd be better off picking the one that has the lower power so you'd have less conversion.
Gotcha.
But yeah, so as long as one of them is odd, you can pick either one will work, but picking the one with the lower odd power is the
Because I
best.
noticed for your thing, you say if one of the powers is odd, it's just if either of them is odd.
Yes.
So whichever one's better.
Yeah.
Not if specifically one is odd.
Good point.
Okay.
Good point, yeah.
Was curious about that.
Yeah.
Maybe
Now-
it's still working.
And if both powers are even, that's worst case scenario, then you have to just power reduce both of them. So we already know that if we integrate sine squared, or if we integrate cosine squared, we use those two power reduction identities. If both of them are even, you just have to use power reduction on both of them.
What if it's 0?
I love integrating 0.
Power of 0 is just one. Just
Integrating
one.
of 0 is just so pleasant. So quick. Okay, secants and tangents are more complex, obviously. All right, so we're going to treat it, there's two main strategies. If the power on secant is even, we're going to pull off secant squared. If we pulled off secant squared, what would we want to let u equal?
Tangent.
Tangent, because the derivative of tangent is secant squared. So that tells us that, oh, well then we need to convert the leftover secants to tangents so that when we let u be tangent, we have all the tangents replaced with u's. So if secant is to an even power, we can pull off secant squared. All right, and so what that tells us, if secant is even, if the power is even, we pull off a secant squared, we still have an even number of secants. So they can be converted with the Pythagorean theorem. The Pythagorean theorem only converts even powers. All right, now the other case here, if the power on tangent is odd, then we want to pull off a sectan. So if we take off a secant tangent and put it with the differential, what do you think we want to let u equal?
Secant.
We want to let u be secant because the derivative of secant is secant tangent. So if we pull off a sec squared, we want u to be tangent. If we pull off a sectan, we want u to be secant. All right, so we look at this thing, it's like, oh, even power of secant, there's not an odd power of tangent, so we only have one option. We're going to pull off the secants. So pull off the secants, and convert leftovers. Well, if secant's raised to the second power, are there any leftovers? No. If secant was to the fourth power, we'd have leftover secants and we would want to convert those. So when we say convert, we mean convert any of the leftovers that were left behind from what we grouped with the differential. So really here there's nothing to do, but I'm just going to sort of I'm just going to visually move the secant squared over to the right and think of it as grouped with the differential. So we didn't have to convert any leftovers, and we already said that, oh, now we're just going to let u be tangent. So if u is tangent, then what is du?
Secant squared.
Secant squared multiplied by dx. So then this all becomes just quite simply u squared du. So we get a third u cubed. And then we just have to replace the u with tangent. So we get a third tangent cubed of x plus c. So even power of secant, pull off a pair of secants. Convert any leftover secants. Okay, now we have, I think that's the last one on this page. Now we have a tan raised to an odd power. So the rule says if tangent is to an odd power, pull off a sectan. And you say, oh, there's no sectan there. There's no sec. We have learned to conjure up functions whenever we need them. If we need a secant, we create a secant. But if we create a secant, we have to divide by it to preserve the balance. We need to, so here's what we're going to do. It's like, okay, well, tangent is to an odd power. Now I know I need to pull up a sectan. Oh, but there is no sec. We create one. Right? So we do that. That's just multiplying by 1. It's our favorite trick, multiply by 1. All right, so now the rule says pull off a sectan. So we think at least conceptually that the sectan is sort of becoming part of the differential. It's becoming one with the differential over there. So pull off a sectan. And what did we say we wanted to let u equal?
Secant.
We want to let u equal secant because the derivative of secant is secant times tangent. So if we're going to let u be secant, what we have to keep in mind is that we've got to convert the leftover tangents. So our rule was if tangent is to an odd power, pull off sectan. So when we talk about the leftovers, we mean the leftover tangents. So we're going to think of this as tangent squared. All right, we'll put this intermediate step in just to make sure. So we have that. So we pulled off the sectan. These are considered the leftovers in this case. Those are the ones that are being left behind. So those are the ones that get converted. So now we want to go back to that identity that I showed you, this circle, which is really the best visual way to remember this identity. So there is the circle that gives us this identity. This is 1. That's tangent. And the hypotenuse is secant. So this is the identity. So if we want to convert tan squared is going to be secant squared minus 1. Secant squared minus 1. So that'll be secant squared minus 1.
Secants cancel.
Secants cancel. Oh, I guess I already have an equal sign over here. That's a little, let's move it over here a little. Okay, so tan squared, secant squared minus 1. Actually, secants, we really don't want to say they cancel.
That's true.
We could split the fraction.
Yeah.
But we're at the step where we want to do our substitution first. So we group the secant with the differential, thinking ahead that we wanted to let u be secant. So we're going to let u be secant. So du is sectan. You could do this algebraic fraction splitting now if you want. It's always easier to turn it into u's before you do any of that stuff though. Then you're not rewriting, a bunch of trig functions. All right, so let's do our substitution. So we're going to have u squared less 1 over u. And then,
You're not.
what is that? Huh. Is that not ink? Oh, it is. That's weird.
Erase.
It was ink, but it didn't seem like I wanted to be erased. So that's u squared minus 1 over u, and then du. Now, last class we talked about one of those oddball things where you had an improper fraction. Right, this is top heavy. But it actually, so you actually can do the division though instantaneously without long division, right? You can just split the fraction.
It's just if you can't split the fraction.
If you can't split the fraction,
It's not that.
then you would have to do long division. Here we can just split the fraction. So we can say divide the u into the u squared, divide the u into the 1. We're good to go. Now we have a proper fraction, no issues. The integral of u is u squared over 2. What's the integral of 1 over u?
Natural log.
Natural log absolute u plus c. The only thing left to do is back sub. So we have to remember that we let u be secant. So now we just replace the u's with secants. So we have 1/2 secant squared of x minus natural log of absolute value secant x plus c. Voila.
So in the yellow, if it was like u plus 3, then you have to do long division, because you can't divide.
If it was u plus 3 in the numerator?
Yeah.
So-
No,
Denominator.
If it was u.
Oh, gotcha. So if we had this,
Yeah, something like that.
so if we had that, then we would do long division.
Okay.
But you still could split the fraction here. You actually could split the fraction like this if you wanted to, and then just do the long division here is possible.
Okay.
Or you could do it there, doesn't matter. But yeah, you would have to do long division.
The long
You would-
division matters most when it's just a single term at the top.
When it's a single term in the denominator, you don't have to deal with it. Yeah, then you can just split the fraction. But yeah, you're right. You would have to use long division in a case like that if this is multi-terms. Multi-terms.
What was that third fact though?
So the third, if the power, so we have a rule if the power on secant is even, or if the power on tangent is odd. So this just says, if the power on secant is odd, okay, so we can't use 1, and the power on tangent is even, so we can't use 2, then we want to convert with Pythagorean identity. So convert the tangents.
It didn't select right.
So then we just want to convert the tangents with Pythagorean identity.
So for everything in a sequence, and then you end up with a.
And where we're converting the tangents because they have an even power, so they can be converted.
Gotcha. And then you.
And then there's a whole myriad of things that can happen. So usually, we hope that we don't have to. In that case, usually it will just come unraveling with Pythagorean substitutions, usually.
Okay.
So the two main cases, secant, even, tangent, odd. Those are the main cases. So let's take a peek.
Yeah, so what happens? You just figure it out. I think you're in 8.4 before, and we were.
Yeah, we're supposed to be up here somewhere.
Yeah,
There.
there you go.
There we go. All right, so here's one. All right, you all want to try this one? So this has both cases satisfied, tangent to an odd, secant to an even, so you could do either. Which one makes more sense? Which would require less work in converting leftovers?
Secant squared.
Yeah, if you if you pull off the secant squared, you only have to convert a secant squared. If you pulled off a sectan, you'd have to convert tangent to the eighth. Which you could do, but that's going to be more work. So go ahead and try this one and use whatever you want, but probably pulling off the secant squared is going to be the easiest.
It just should be 1 plus u though, right? Not 1 minus u, because it's just, which makes it, just changes one single sign, but. I had to do the chart of Pythagorean densities to get it right.
So if we pull off a secant squared and group it with the differential, the conversion of the leftovers, we're left with a secant squared. Again, there's our picture for the secant tangent identity, which is a really good thing to just have in your mind. It makes things a lot simpler. Instead of going back and doing the algebra every single time, that gives you a nice visual for what's happening. So you look at that, right triangle, secant squared is tan squared plus 1. So tan squared of theta plus 1. And then the secant squared is grouped out here with the differential. Then we're going to let u be tangent, because its derivative is now that thing that we grouped with the differential. So we're going to let u be tan of theta. So du will be secant squared of theta d theta. And we're going to have the integral of u to the 9 times u squared plus 1 times du.
See, just excited to convert to u, so I don't have to write theta 3 times.
Right? Right theta.
Become just an O with a line through it.
O with a line through it. Can't they just always use x?
Yeah. Just honestly, multiple times we'll just convert everything to x's if it's non-relevant thing. Like for volumes, it doesn't work as well, but
And then I sit there and I wonder why MATLAB's getting so upset. It's like, why aren't you accepting my answer?
Oh, yeah, because I converted everything.
Because you didn't use
It's
a
supposed to be
Y.
theta.
It's 1/12, 10 to the 12, right?
Somehow.
Incorrect, your answer, 3x, correct answer, 3 theta.
Yeah, I've seen that before.
Yep,
Tangent theta plus
that'll drive us crazy.
plus 2.
All right, does that make sense to everybody?
I got it right.
Woo! Any step there you want to ask about? All right, one more on this slide. This is not considered an even power on secant. When we say an even power on secant, we mean in the numerator. Right, this thing is in the denominator. So this is a tan cubed of theta over secant squared. So the whole idea is that you're pulling something off that can be grouped with the dx or the d theta or whatever, the differential. That is not an even power on secant. So we have to treat this as an odd power on tangent. And again, if we have an odd power on tangent, we pull off a secant times tangent. Well, there's no secant in the numerator, so we conjure. We've now conjured up a secant for the numerator. So tan is to an odd power. We're going to pull off a sectan and convert the leftovers. And by leftovers, we mean convert these tangent squareds right here. So this is where we're at after we pull off a sectan. So that sectan is pulled off, grouped with the differential. Now we have to convert, these are considered the leftovers because we're doing a tangent thing. These are the leftovers. So those are the ones that need to be converted. And we already know that tan squared, if we look at our identity, tan squared is secant squared minus 1. So secant squared of theta minus 1 over secant cubed times secant tangent. And what are we going to let u be? Secant? It's what we turned the integral into, a bunch of secants. So if we're going to let u be secant, then du secant tangent d theta so it's always easier to convert over to your u's as soon as you can. Yeah, ooh. Oh, how about that? All right, so any issues on getting converting over to u's? The denominator is the single term, so we can split it. So we can split this fraction. U squared over u cubed is 1 over u minus, we're going to write that as u to the negative 3. It'll be easier to integrate. So we are splitting, so we're sharing the u cubed that way and that way. Integration. Natural log absolute u minus, add 1 to the exponent, divide by the new exponent, so that's going to put a multiplication of 1/2 out in front.
Negative 1/2, and then I combine with the minus.
And then we're going to end up with natural log absolute value of secant of theta plus 1 over 2u squared, so that's 2 secant squared. That's supposed to be a plus c. Plus c. And if you wanted to, secant in the denominator could be moved to the numerator and turned into a cosine. So the simplest answer here is probably going to be written in my math lab like that. Eek! So this section is not that difficult. This section's, fairly straightforward. A little bit of practice, obviously, super important, but if you put in the practice, it should be reasonable. Here are a bunch of identities that you should never even attempt to memorize, unless you are a wingnut. I have had wingnuts in this class that memorize those things. You do not need to memorize the power reduction identities except for sine squared and cosine squared. Those are the only two that we use so frequently that you really do need to memorize. These general power reduction identities you do not need to memorize. If I wanted you to do one of these with a higher power than 2, I will give it to you. But you should be able to use them if they were given to you, so let's try one with secant to the 5th. I mean, it feels like we're no longer doing math. It feels like we're doing, cooking or something.
Physics.
Or physics. I didn't say that. So secant to the 5th, we're looking at this one here. So the idea is that we just have to follow this rule over here, and it says, okay, ratchet down the power, decrease the power in the denominator, blah, blah, blah. So the denominator is going to become a 4, because n is 5. This is going to be secant cubed of x times tangent x. So the way that these formulas came about is with integration by parts. So you could do integration by parts to get to this. And then this will be 3/4 integral secant cubed of x dx. So now we're there.
Did you just rinse and repeat?
And then we rinse and repeat. So we do that again. So secant is now to the 3rd power. So we're going to do this again. So we've got this stuff out in front. And now n is 3. So 3 minus 2 is 1. So we're going to get a 3/4 multiplied by secant times tangent divided by 2 plus, n is 3 now, so that's going to be 1 over 2 integral of secant to the 1. Let me know if there's a step there you're not totally tracking. And now we talked about the integral of secant. One thing I pointed out was that other than sine and cosine integrate to each other. The other 4, cotan, tan, cosecant, secant, they all integrate to logs. And that one we said, so this is going to be 1/4 secant cubed tan x. So what we said was that this one integrates, does anyone remember what that one integrates to?
1 over square root of 1 plus x squared?
Natural log of absolute value secant plus tangent.
Inverse.
Yeah, the inverse, yeah, that would be different if we were. So if we just want, so the interesting thing with secant, so we did this, we did this the other day. The integral of secant, you have to multiply top and bottom by something that puts it in logarithmic form, and it turned out that we multiplied by secant plus tangent over secant plus tangent. Back, I think it was on Monday, Tuesday. It was somewhere over here. Yeah, I don't remember where. Doesn't matter.
Complete the square?
Say again?
How we complete the square of miscellaneous?
Is that where it was? Yeah, it's somewhere in there. I just don't remember.
Maybe it's not. Maybe it's-
Yeah, maybe we did it the previous day. No, that was a test. I thought we just did
Was it at the
it.
beginning of the demonstration by parts or no? No.
Maybe it was at the, I don't know. I don't remember where it was now. But regardless.
Is it just basic approaches?
Oh, yeah, that's where it was. Thank you. Basic approaches. Yeah, so if we integrate secant, we multiply top and bottom by sec plus tan, and it turns into natural log of sec plus tan. Which you will see a bunch, enough in the homework that you'll probably get to the point where you just start writing that down automatically. Okay, so we'll go ahead and stop there. Time for a weekend? Ish?
Whoa, I
Close.
got a physics test before the weekend.
Today or tomorrow?
Tomorrow.
Tomorrow. Oh, perfect, so you can have like a 3-hour block?
Yeah.
Yeah, lucky you.
I've got a.
Actually, I don't know, do we have the whole period for the physics test?
I think it's 1 to 250, so it's close. Probably got time.
All right.